In this video, we're going to discuss oxidation and reduction reactions. Your typical reaction to form an ionic compound, say taking lithium metal plus chlorine gas to produce lithium chloride, and we would need to balance that, of course. In these types of reactions, our lithium actually reacts to form lithium plus 1, and in order to do that, it gives up 1 electron. Whereas our chlorine will react with 1 electron per atom in order to produce 2 chloride ions. All right? Basically then, what's happening is our lithium is giving up an electron, 1 electron per lithium. So if we were actually going to balance this, we would put a 2 here, a 2 here. We would put a 2 there so that we would end up with our balanced redox or oxidation reduction. Another name for an oxidation reduction reaction would be a redox reaction, which is just a way of putting together this term, oxidation reduction. Now, when we're looking at this, what we would say is we would say that the lithium is oxidized. So this is the oxidation half reaction. And the chloride is reduced. So this is the reduction half reaction. A mnemonic to remember this definition would be oil. So oxidation is loss, and rig, which is reduction, is gain. Here, our chlorine is reduced and our lithium is oxidized. So let's say that we look at another equation. We're going to look at the oxidation of iron to form rust. And if we look at this equation, in order for us to determine what species is oxidized and what species is reduced, we first have to understand what the charges or oxidation numbers are on each one of these species. And there are different rules that we will use to do this. Rule 1 is that all elements in their base elemental forms have oxidation numbers of 0. In this case, if we're looking, here our iron, well, that's metallic iron. It's in its base elemental form. So our oxidation number for iron in this case is going to be 0 here on the reactant side of our chemical equation. If we look at the oxygen on our reactant side of our chemical equation, oxygen is part of Brinkelhoff. So it's one of those elements that is diatomic in nature. I don't know if you remember Brinkelhoff, but Brinkelhoff stands for hydrogen, HOF. Okay, this is bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine, and they all form diatomic or 2 atom molecules in nature. This, therefore, our O2 is our elemental form of oxygen right here. So its oxidation number on the reactant side of the equation is also 0. All right. Our next rule then is that the oxidation states of monoatomic ions monoatomic means contains only one atom, is the charge on the ion. Here, in this case, we have F2O3 that we're looking at. In that case, just like we would do our reverse crisscross method that we did when we were naming and formula writing, our oxygen on the product side is oxygen. When we look on the periodic table, it makes a -2 charge. So that's going to be our oxygen. So that means that we have 3 times -2. And as always, when we're making a formula, the sum of the charges has to equal 0. That means that R2, because there are 2 irons here, times the charge of the iron, plus 3 times -2 has to equal 0, so that our charge on the total formula is 0. So that means that our X has to be -3. So that means that the oxidation number of our iron has to be +3. If we're going to write our sort of half reactions for this, that means that iron, for each iron, it is reacting to produce iron plus 3 electrons. And our oxygen is going to add 2 electrons per oxygen atom. So that's 4 electrons total. That's going to make 2O minus 2. Now, if we were going to put these two together to make a balanced chemical equation, basically the chemical equation that we had here up at the top, this one, then we'll have to multiply by these, and the number of electrons that all of the irons give away should equal the number of electrons that all of the oxygens take up. So if we do that, we want these numbers to be equivalent, then 4 and 3, their least common multiple is 12. So we're going to make that 12, and in order to get 12, we're going to have to multiply this times 3, and that's going to have to be 6. We're going to have to get 12 here. That means we're going to have to multiply this times 4 and that times 4. And if we added those two things together, normally when we do this, we just cross out what's the same on both sides of the equilibrium arrow, because those are just spectator things. So we get 4 irons plus 3 oxygen molecules react to produce 2 Fe2O3. This is the equation that we had up at the top. Now, if we look at this reaction right here, iron has electrons as the product. So since this has the electrons as the product, then the iron half reaction is the oxidation half reaction. That means that iron is oxidized. Now, in this lower half reaction, the electrons are a reactant, which means that oxygen is gaining electrons. So this is reduced, and this is our reduction half reaction. All right, now if we come back and look at these two half reactions, there's another definition that you need to know, which is that the element who is oxidized is the reducing agent. So this is a little counterintuitive, okay? In this case, we have iron that's oxidized, okay? It has lost electrons. Remember, oxidation is loss. And since this one is oxidized, it is the agent of oxygen's reduction. so it is the reducing agent. Similarly, the element who is reduced is the oxidizing agent. If we're looking here, oxidation is loss, so that means iron is oxidized. Reduction is gain, so the oxygen gains electrons to produce oxide anion. And since oxygen is reduced, it is the agent of iron's oxidation. Another way to remember this is that oxygen is usually going to be the oxidizing agent. And the reason that it got that name is things that are oxidized oftentimes will end up in a compound with oxygen on it at the end. So that's one of those things to look for to help you identify who's oxidized and who's reduced. Almost always oxygen is reduced and iron is oxidized. Now, so far, we have discussed two of the rules for how to determine the oxidation states of atoms. There's a couple of more rules that we will want to know so that we can employ them. The third rule is that the sum of all the charges of the atoms or ions, or the sum of all the oxidation states, sometimes charges and oxidation states are used interchangeably, although not all oxidation states are charges. But the sum of the oxidation states of the atoms in a compound are either 0 if the compound is neutral, or the charge on the charge on the polyatomic ion, assuming that you have a polyatomic ion. Rule number 4 states that oxygen almost always forms a -2 charge. And for the purposes of the nursing exam, that rule will apply. Elements in back or in rear tend to make the charges predicted in the periodic table. Rule 5 states that group 1 and group 2 elements, or groups 1 and 2, form the charges predicted by the periodic table. Just as a reminder for what those charges are, if we look at our periodic table, if you'll recall, groups 1 and 2 tended to make group 1 made a +1 charge, group 2 made a +2 charge. Now, if we look at group 4, or rule 4, where it says that back end elements, and I'll explain what back end means in a minute, form the charges predicted by the periodic table. That is here where nitrogen or the group 15 makes a -3 charge, group 14 or group 16 makes a -2 charge, and group 17 makes a -1 charge. So here, let's use these rules to determine oxidation numbers of elements in 3 polyatomic ions. The first polyatomic ion, this one's nitrate, and we're talking about back-end molecules keeping their charge that's predicted by the periodic table. So if we look here, nitrogen's at the front end of this polyatomic ion, but oxygen's at the back end. So oxygen is going to make the charge we predict off the periodic table, which is a -2 charge. Now there are 3, because of here the subscript 3, -2 charges. So we have 3 times -2, and there we're using rule 4. Using rule 3 states that all the charges have to add up to the charge on the polyatomic ion, or the 0 if it's a neutral compound. This is not a neutral compound, it's a polyatomic ion. type of compound. So the overall structure has a charge of -1. So that means that we have one nitrogen, and we don't know what its charge is or its oxidation number is, and we have 3 oxygens. Each oxygen, because it's at the end or the back of the compound, is going to have a -2 charge, and the total of the charges on the compound has to equal this -1 value. That's where it's coming from. So basically what that means is that our oxidation number on nitrogen must be +5. Now this is very different from what it is on the periodic table, and that's because this is sort of the, well, our way that we write it is that we always write the one that can change charge in front if it's a polyatomic ion, so that we know which one we're looking for. So if we look at the second example, which is sulfate, our oxygen again is going to be -2, because oxygen is always going to make a -2 charge for compounds that you would typically see on a nursing exam. So the most of the common compounds, peroxides would be the biggest exception. We've got 4 oxygens. Each oxygen has a -2 charge, so that's times -2. We're going to add that to our 1 sulfur, and our sulfur, we don't know what its charge is, so we're going to put that as X, and it has to equal a total of -2 because that's the charge on my sulfate ion. That means that this is X plus -8 has to equal -2. So our X value, or the oxidation number of sulfur, is going to be +6. Again, sulfur, if we look at the periodic table, we would predict that would make a -2 charge, but because it's the front element here, we're going to say that it's a +6, and it can change charge. Last but not least, we have chlorine, and our chlorine, again, our oxygen's going to make a -2 charge, and we have 3 of those. 3 times -2, we have 1 chlorine, so 1 times X, because we don't know what the charge on the chlorine is going to be, equals our total negative charge for the polyatomic ion is -1. This is X minus 6, or plus a -6 if you want to say, is -1. So here the oxidation number on our chlorine is +5. Here are some other neutral compounds for us to determine oxidation numbers of. If we look at carbon dioxide, CO2, again, our oxygen is going to have a -2 charge. There are 2 -2s, so that 2 goes there. This -2 goes there. Added to, we have 1 carbon, so 1X, because we're not sure what the charge on our carbon is going to be. And because there's no charge on this ion, then we're just going to say that this equals 0. And so this is X minus 4 equals 0. So our carbon has a +4 charge, which is unsurprising because that actually is one of the charges that we would predict from the periodic table. If we look here at water, again, our oxygen is going to be -2. Our hydrogen pretty much either forms a +1 or a -1 charge. In this case, we have 1 times -2 and 2 because we have 2 hydrogens here. So 2x plus -2 equals 0. So X is going to be 1. So we have a +1 charge or a +1 oxidation number on our hydrogen. And last but not least, if we're looking at ethane, which is this compound right here, we have hydrogen, which is going to make a +1 charge. We have 6 of those. So 6 times +1 equals 0. And then we've got 2x, because we're not sure what our carbon oxidation number is going to be. So that's going to be our C here. And so that means that each carbon has to have a -3 oxidation number. The examples that we've done on the 2 previous slides were covalently bound compounds. Now let's do a couple that are more ionic so that they have a cation paired with a polyatomic anion. So in this case, here we have phosphoric acid, and we know that this is an acid because it has an H in front, and usually compounds that have hydrogens in front are acids, with the exception of water. And we can reverse crisscross that, or say, okay, we know that hydrogen always makes a +1 charge, and there's 3 of those. So we have 3 times +1. We know oxygen always makes a -2 charge. That's +4 times -2. And we have 1 phosphorus, so that's +1x, because phosphorus is going to be the one that we don't know the charge for, because pretty much anything that you're looking at that has generally 3 atoms in it is generally going to have a polyatomic ion. So you're going to look at whatever is the front element, and that's going to be your cation, so to speak, and the back elements are going to be part of that polyatomic ion. And our total charge, because we don't have a charge listed here, is going to be 0. So that is 3 plus x minus 8 equals 0. That means that our phosphorus has to be +5 is x. So we have P minus or +5 and O -2. And those are the oxidation numbers of all of our elements in this compound. So if we look at sodium sulfate, now this is a truly ionic compound. Again, our sodium, that's a group 1 element, so it's always going to make its charge off the periodic table. So there's 2 times +1, because there are 2 of these. Plus there's only 1 sulfur, so we're going to say that that's 1 times x, plus 4, and our oxygen always makes a -2 charge, so that's times -2 for this. And we don't have a charge up here, so this all has to equal 0. So that's going to be 2 plus x minus 8 equals 0. So our sulfur is going to be a +6 oxidation number. Please determine the oxidation numbers of each element in both of these molecules. Pause your video, complete the work, and I will return in 10 seconds with the answer. So in our top compound, hydrogen has +1, oxygen has -2. It's neutral, so that is 2 times +1 plus 1x, because there's only 1 carbon, plus 2 times -2 equals 0. That means that my carbon must have, this is -4, 2 plus x equals 0, a +2 charge or oxidation number. For our second case, nitrogen, the oxidation number is 0 because it's in its elemental form.